Good afternoon, judges and everyone. I'm Chu Yang. First of all, I really appreciate this opportunity, and I hope today everyone can enjoy this series of presentations and speeches. Just as some self-introduction, I'm a first-year PhD student from NUS Mechanical Engineering, and my research interests are currently in materials as well as additive manufacturing, aka 3D printing. I know material and manufacturing sound just like typical NE stuff, but as you can see from the title, today I would also like to touch upon some area that I find in myself really exciting as well as meaningful to our everyday life in terms of treating diseases or even saving lives, and that is bone tissue engineering. Without further ado, today I would like to share part of a literature review that I've been working on, and I know the title can be quite a mouthful, robocasting of calcium phosphate scaffolds for bone tissue engineering applications. But we can start with breaking it into smaller parts by asking, first of all, what is bone tissue engineering and what is bone tissue engineering scaffold? Then with this targeted application in mind, we can take a look at the material as well as the process. And then I would like us to take a deeper look at this problem by asking how well can these robocasted calcium phosphate scaffolds actually perform in a way to see why we are using this specific material and this specific AM process. Lastly, let's not forget this is supposed to be a presentation about mechanical engineering. So I would like to look at this problem from a mechanical engineering perspective and to see how we can further improve these scaffolds for future commercial or even clinical usage. First thing first, what is bone tissue engineering? If I were to ask how critical bone is to our body, I believe it's not a difficult question, especially for those who've had bad experiences of having minor bone fractures while doing sports, and they have to have this plastered for weeks or even months. Well, speaking of the functions of bone, it provides mechanical support for our body as well as protection for internal organs, especially those very vital ones that to our body. And as of now, I'm doing all these hand gestures, all thanks to the bone that allows the movement of our body, etc., etc. As bone is so critical, the nature has designed it in such a way that it's going through constant modeling and remodeling process to keep the bone fresh, strong, and adaptive to the environment. Despite these capabilities, in cases of a large bone defects, which the bone would take a prolonged period of time to heal or even couldn't heal at all, these are the times that we need external intervention, uh, including autograft, allograft. These two are the more developed and established treatments over the years, but they have their own limitations as well. For example, autograft can cause secondary operations or even donor site morbidity issues, while in the cases of allograft, there's a risk of disease transmission and it's subjected to availability. In light of all these issues, BTE is therefore a developing but promising alternative to overcome the limitations of the current treatments we have. And unlike the metal implant that we are probably more familiar with, bone tissue engineering solution is not just simply replacing the missing bone tissue with something else. It's more like how we can use a certain device to simulate the bone healing process. So at the end of the day, as you can see from the left-hand side, the graft will gradually degrade and being resolved, while on the right-hand side, simultaneously, we have our bone tissue gradually regrown and regenerated. So at the end of the day, this scaffold will be completely removed out of our body, while the thing that's filling the defect will be the newly grown healthy bone. As you can probably imagine, this is a very dynamic and yet complex process. And in order for us to achieve that, scaffold is a very little device that provides not only temporary support, but also promote the cell activities and stimulate bone regeneration. And here is a long list of different requirements for such a BT scaffold to actually work. And I've characterized them into biological, structural, as well as mechanical aspects. And just be reminded that this is probably not an exhaustive list. I know it's long, but it's not exhaustive yet. Just imagine if this BT scaffold were to be put into clinical use for human beings, there's definitely more things to consider. But these are just the most fundamental ones that a lot of researchers and recent studies have been evolving and circling around. And if we look at the biological performance first, in fact, there's no better way than just simply use a bioactive material to achieve the biological properties that we want. And yeah, you probably have guessed this is where calcium phosphate comes into play. And calcium phosphate has a over 50 years history as bone substitute material. And more recently, major inches have been developed of using it as a BT scaffold material. And the reason is obvious. It just happens to be the primary mineral content in our bone, as you can see from the schematic, the diagram over here. This mineral crystalline apatite is just chemically calcium phosphate. But of course, when we're talking about calcium phosphate as a biomaterial, we're referring to a family of bioactive ceramics that comes in different forms, including HA, beta TCP, and biphasic calcium phosphate, or shown as BCP, as the most popular ones. And these calcium phosphate materials exhibit very good biocompatibility, bioactivity, as well as osteoconductivity. And if you still recall, these are just exactly what we want for the biological performance of our BTE scaffold. Okay, this looks all promising from a biological point of view, but if we also take a look at the mechanical properties, where you can see from this map that calcium phosphate is still intrinsically or basically ceramics. And we know that ceramics are hard or brittle. So this brittleness is reflected in this graph as there's a mismatch of this fracture toughness when we are comparing calcium phosphate with this green area, which is basically the natural bone. So this mismatch of mechanical property is definitely something that bone tissue engineers must consider in real life applications. But just be reminded that if we are talking about the mechanical performance of the scaffold, it's not only dependent on the material, but also dependent on the structure and the process as well. So this is where we have also take a look at the manufacturing process, in this case, robocasting. In a nutshell, robocasting, or sometimes referred to as direct ink writing as well, is an additive manufacturing technique based on the direct extrusion of a certain paste through our nozzles. And so you can see here is a schematic diagram of a typical workflow of robocasting process, where we started with preparing the CAD model and preparing the specific ceramic paste that we want, or in this case, the calcium phosphate paste, and followed by the robocasting process, whereby these pastes were extruded line by line and layer by layer on a substrate until it forms the lattice structure that we want. But we haven't finished yet. This green body, this printed lattice structure, will also have to go through a series of post-processing process, including drying, debinding, whereby any organic compositions in the ceramic paste will be removed, as well as sintering, whereby the green body actually undergoes significant densification. So the density actually can go up all the way up to 90%. Now that we've had this sintered ceramic lattice, let's take a look at how well can these robocasted scaffolds actually work. Probably most of you are also interested to find out. This is a SEM picture of a robocasted lattice structure, whereby you can see that there's both micropores in between the struts, as well as micropores on the surface of these single struts, or even within the struts. Actually, these two types of pores perform different biological functions. In terms of micropores, they facilitate cell transport, cell migration, as well as vascularization, which is basically blood vessel formation, as well as tissue ingrowth. And these pores are pathways whereby nutrients can come in and supply, as well as the waste can be removed out of this defect site. In terms of the micropores, they are more like small anchor points for the protein as well as cells to attach and absorb onto the surface, and therefore facilitating the bone tissue ingrowth. If we take a step further by looking at studies that in vitro as well as in vivo study the biological performance of these HA and beta TCP scaffolds, they exhibited very good biocompatibility as well as promoted cell and tissue ingrowth in vivo, and exhibited osteoconductivity in pig maxillary defect implantation model. If you refer to these two diagrams where you can see these robocasted calcium phosphate scaffolds actually produced very comparable results uh, compared with the clinically used porous structures. So this shows actually the great potential of our BT scaffolds. Next, I'd like to share a very interesting veterinary clinical case by this little cutie Yorkshire Terrier was treated with a robocasted beta TCP synthetic bone scaffold. If you refer to this radiographs, whereby the leftmost one is directly taken right after the surgery, and the rightmost one is 5 months later, you can see that degradation or resorption of these scaffolds, and also simultaneously a progressive healing process of the bone. So if I'm not wrong, actually 18 months after the surgery, all these compression plates were also removed. In 36 months, the veterans actually diagnosed the complete healing of the bone and a complete recovery from this bone fracture for this Yorkshire. Although all these results seem really promising, there's still a long way to go for us to actually realize real-life clinical use for human beings. In terms of all the limitations and challenges faced by these scaffolds, next I would like to take a mechanical engineering perspective to see what are they and how we can further improve upon. Here I just use compressive strength as one example, as compression is probably the most relevant type of loading that the scaffold would experience after being implanted into our body. And here is a picture of such a scaffold about to be compressed by the machine during the compression testing. And on the right-hand side is actually a graph of the experimental data collected in the literature of different robocasted calcium phosphate scaffolds, showing their compressive strength and porosity. As we can see here, there's a strong relationship between compressive strength and porosity. With increasing porosity of the scaffold, the compressive strength would decrease, and this makes perfect sense. As the more porous the structure is, it becomes more easily to fail under compression. Well, another way to look at this graph is that if you notice this gray band area, which I've noted as cortical bone and a cancellous bone. If you're aware, cancellous bone are the spongy or soft part of our bone, while cortical bone is the more impact and much stronger part to sustain load. And you can see that most of these scaffolds, robocasted, showed compressive strength only comparable to the spongy soft bone. This means they cannot really sustain from medium to high loading. Therefore, this poses great limitation to their application. And the research and studies have been focusing on how to improve the compressive strength of these scaffolds in order to broaden its application in the future. In face of this kind of problem, there are actually typical directions that we can approach, namely from a structure perspective, process perspective, and last but not least, a material perspective. And here I just cited a few examples as a demonstration of how mechanical performance of these scaffolds can be improved. The leftmost picture is actually a graded pore distribution design for such a scaffold. As you can see that the pores are bigger inside compared with the outer ring of the scaffold. So this is actually a biomimetic design of how our bone looks like, whereby this surrounded by a compact shell, while inside is more spongy and porous. However, there's still not yet a systematic study or systematic evaluation on the mechanical performance of such a kind of structure. And in the same time, if we were actually to use modeling as well as simulation tools that help us find the optimal scaffold structure, and that's another way to help us improve the mechanical strength of these scaffold. Next comes the process. If you still remember, sintering is one of the post-processing where the scaffold gains great densification as well as a mechanical strength. And if we were to use different sintering techniques or control the sintering parameters, we were to see higher densification or finer grains that can help us improve the mechanical strength of these scaffolds. And last but not least, material. If we were to use some reinforcing additives into the material, we might see some increase in the mechanical performance. And this picture is actually a composite material whereby the core are actually filled with biopolymer, while the outer shell is the bioceramic, the calcium phosphate. And in this way, this biopolymer is more ductile, adding another phase to help this whole structure sustain load and being resistant to fracture upon being compressed. And to summarize today's presentation, if you still recall, the requirements for BT scaffolds actually can be characterized into biological, structural, and mechanical aspects. And in today's presentation, I've already talked about how calcium phosphate can help us achieve the biological properties and how ribocasting can allow us to control the porosity as well as the pore size and pore shape. And lastly, there's still a gap, a limitation in terms of the mechanical performance of these scaffolds. And this is where mechanical engineering can come into play. And as I'm put up right here, MV is relevant. Well, I hope you'll find my presentation interesting at least. In fact, I hope this is a good example of how ME can collaborate or can come into play with other different areas such as tissue engineering. And in fact, these days people have been talking about interdisciplinary cooperation. In this case, whereby material researchers, mechanical engineers, tissue engineers can all come into play to tackle this problem. This is how we can bring the idea of BT scaffold forward towards future clinical or even commercial usage. With that, I'd like to conclude my presentation and thank you. And if you have any questions, I'd love to help.